Buddy. Oh, okay. Anna was questioning whether anybody would show up again for day 2. And so I hope that you all had a good day on the town in Rotterdam last night. Everybody have a good time? I only saw some of you at the beer boutique, but hopefully I'll see others of you there probably again tonight. All right, so Victor, we got most everybody? Yes. Okay, all right, so we got some attrition, but some of you came back. So you were the ones I liked better anyway. So welcome back. So today we've got about 2.5 hours, and yesterday we worked through the process of creating concept sets and creating cohort definitions, and today we're going to go through the process of evaluating those cohort definitions. So I want to first give a special shout out to Gowtham, who's one of our faculty members who's not physically here. He's based in the US. But last night he took all of your definitions and ran them across 4 databases, and you all now have access, and we'll go through how you're going to have access to be able to review all of your definitions across a network of 4 databases that were chosen just to illustrate the process. So what we're going to do today is Anna is going to walk through the process of cohort phenotype evaluation and thinking through measurement error. And we're specifically going to highlight the use of one tool called cohort diagnostics. And that is just one of multiple tools in our community that is focused on the problem of understanding measurement error. But you guys will get hands-on experience of being able to use that tool and become familiar with how to use it. Things that we're not covering today, though I'm happy to catch up with anybody who's interested or curious about it. So we're not going to show you how to implement cohort diagnostics to run it on your own data. There's actually multiple tutorials out on the OHDSI website of how to do that. But just so you know, this tool, cohort diagnostics, is just an R package. And what you basically do is you point it to your common data model, you pass in an input, which is one or more cohort definitions, and then it runs a series of analyses and then provides an R Shiny application at the end that you can click through and explore the results. What we're gonna do is just give you direct access to a URL that is the R Shiny app, so you have all the results. But if you're interested in how do you go back home to your own organization and run that, there's other tutorials that we can refer to you for that. We're also not going to cover the other tools that we use for cohort evaluation. Had a couple folks come up to us and ask about other things like, do we have any tools for chart validation or review of patient profiles? We actually have quite a few of those types of tools in the community. Anna has done some great work and has a paper under review about something that I'm really excited about in terms of structuring that process. We also have a tool called Evaluator that allows us to quantify sensitivity and specificity errors. But we're not covering those today, so if folks are interested, I encourage you to reach out, and I can point you to all the references that are out there. Last thing that I'll say before we get started is we hope that you're learning something and getting some experience connecting with each other. You are working on real phenotypes that we actually need done in the community, and some of you all of you made progress yesterday, which is great. Some of you have progress that probably is going to look encouraging, and you're going to say, hey, I think we're almost done with this. Some of you are probably going to say, hey, I probably need to do another iteration or two. But I encourage you to don't just let this phenotype experience end today at whenever we're done. I encourage you to engage and participate in the community and contribute these phenotypes back. Gowtham, who's not here, co-leads our OHDSI phenotype work group, and they meet every Friday, I think it is, to catch up with the community as it relates to developing phenotypes. He's also the maintainer of the OHDSI phenotype library, and basically there is just a straightforward process for you to submit your phenotype and your evaluation, and it is just posted on the OHDSI website for everybody to be able to reuse. And so I encourage you all to take that next step after this tutorial, but you can decide that for yourself after we get through the exercise. So with that, we are going to dive into talking about measurement error. But first, I heard that today is a special day for somebody. And since y'all aren't fully awake, I'm going to ask that you join me in singing Happy Birthday to Ingeborg. Can you stand up, Ingeborg? And hold a flag. All right. So for everybody, we're going to sing Happy Birthday. Ready? Happy birthday to you. Happy birthday to you. Happy birthday, dear Ingeborg. Happy birthday to you. Woo. All right. So hopefully that makes you feel either better or worse about being stuck on a Sunday here at the Odyssey Symposium. But at least you'll remember it for a little bit. All right, so we're going to get started. So Anna's going to walk through cohort diagnostics, talk about measurement error, and we'll specifically, again, we're going to try to illustrate the principles of this with type 2 diabetes. And I think there's some interesting nuggets that you can take away. But the main thing we really want you to take away is the thinking, the process, the tools of how we are doing that for type 2 diabetes, so that when we break out in about 30 minutes or so, you all are going to be prepared to use these processes to evaluate your own phenotypes. And I'll talk about the logistics of that as soon as, once Anna has gone through type 2 diabetes.
So just to remind you, what we started discussing yesterday, right? If you look at the data that we have in each HRSA claims, what we really have is some of the data elements scattered across patient histories, right? Some sort of events, maybe that's lab tests, maybe some visits, people came to clinic and got diagnosed, so it's really timestamps on their history. And what we want, as we said already, is the duration of the periods where those people had certain conditions or diseases. And whenever we want to build those periods or cohort errors, we're effectively want to watch out for several things, right? So as we said already, but just to recap, essentially we want to watch out for three things. One thing is your sensitivity, or not including enough of the cases. And maybe you can have sensitivity problems if you haven't included all of the relevant codes that we spent quite some time discussing yesterday, or maybe because some of the things are not observed in your data. Like, for example, obesity was one of the examples that we gave yesterday, and that can be a classic example because it's oftentimes undercoded in the data, and this is what we know from the literature. We also want to watch out for, in general, for specificity, which is including too many of controls, and that can happen for all sorts of reasons. Like, for example, observing some of the codes that were put in patient history because these were rule-out diagnoses and not the real diagnosis. And then the third thing that we want to watch out for is the index event misclassification, which for some reason does not get that much attention in the literature, but that effectively incorrectly identifying either when patient first had the disease or had a disease, and when the patient ended to have the disease. And all of these things will be discussed today, and we will look at the characteristics of patients, and we'll try to infer all of these three things. But first we want to say a couple of words about different types of evaluation that is used across the community, a broad research community in general. So if you look at the studies that use observational data, you can see the whole spectrum, right? There are studies that do not evaluate phenotypes, do not measure or assess sensitivity, specificity, and index event misspecification at all. And then there are very elaborate studies that do all sorts of things and go extra mile to, in fact, calculate those measures and report them. And of course, that very much depends on the type of journal, the intended use of the study, who is the stakeholder, whether the study is intended to be used for regulatory purposes, and so on and so forth. But essentially, you can think of the spectrum as of going from nothing to very complex estimation of measurement error, and the gold standard so far has been considered to be chart review, where you take a sample of patients that were identified by your algorithm, and somebody with a clinical expertise does the full chart review and assesses whether each patient in this group has a disease or not, and based on that, calculates positive predictive value, because essentially this is the only thing that you can calculate. And this is a common approach. Some people who have time can do more elaborate stuff, like expanding the sample size or doing random selection from your controls or having multiple clinicians. But in general, a common approach, because it's so time-consuming and so expensive, is to take this small sample. And of course, because it's a small sample, it may not be representative of the whole population. So first, we have the problem of time and money spent on chart review, and second problem is that it may not be that reliable as we want it to be, because the sample size may not be representative of the whole population, and then because different clinicians can assess patient charts in a very different manner. So even though it is considered to be gold standard, there are some challenges with it, and in practice, not every researcher, not every study does that. Then we also have a group of probabilistic approaches that actually have been developed to fix this very problem of not being able to evaluate phenotypes fast enough and reliably enough. And one of the tools that OHDSI has in its stack is Phevaluator, which essentially is the tool that builds predictive models to assign the probability of being a case to each patient, and then based off of that, we can in fact compute all sorts of things, not only PPV, but also sensitivity, specificity, and NPV. So this is good and already much better than what most of the studies report. So if you're interested in probabilistic approaches, I would encourage you to check out this tool and the papers on that. And then there is another approach to assessing measurement error, and we will discuss that mainly, is to look at the cohort and assess their characteristics, whether at the cohort level when you look at the aggregated characteristics, or at the individual level when you look at patient profiles, for example. And the cohort, the idea behind cohort diagnostics is that you can compute all sorts of characteristics or statistics about this cohort. And by looking at these numbers, you in fact can compare them to your knowledge, if you have clinical knowledge, to clinical description or to external knowledge, and based on that comparison, you can actually derive some information about the measurement error, about the specificity and sensitivity and index event misspecification of your cohort. And there is a paper that just went out to mid-archive and is submitted to one of the good journals, describing cohort diagnostics in more detail, and I would also encourage you to check out this link and read more about that. And there are a couple of steps, just to orient you what we will be doing for the next 30 minutes. There are a couple of steps that you want to take. You essentially want to, again, look at your concept set when you look at the cohort and its characteristics. You want to see how many patients you got, and then you want to look at all sorts of characteristics of this cohort. What is the time that they spent in cohort? What is their age, gender, year? What are the patterns, temporal patterns, and what are the patient characteristics? And these are just the basic steps, and we will go into more detail right now live. And the first thing that we will be examining is the cohort that we created yesterday, which is an occurrence of a type 2 diabetes condition code. It's a very simple definition, and we will look at whether this definition can actually get us a nice cohort of patients where we are satisfied with its sensitivity, specificity, and index event misspecification, and whether we need to make any adjustments to this cohort. And as we said before, clinical description is something that can guide us in assessing these characteristics. So some of the people, I oftentimes see that when they say, well, I don't have clinical knowledge, how am I supposed to build a phenotype and then evaluate it? Well, the answer to that is a properly written and defined clinical description, because if if it is written well, then you can use this information to guide you throughout all of the steps, not only creation, but also phenotype evaluation. And just to remind you, the things that we'll be looking at are exactly in a clinical description. So what we see is that type 2 diabetes is a common condition, and it is more common in males. We can look at comorbidities that are commonly observed with this, with diabetes, such as age, obesity, not age, higher age, obesity, hypertension, hyperlipidemia. Then we will be looking for the things that should not be present in those patients, such as secondary diabetes or gestational diabetes. And we will be looking for treatments. As we said, these are the drugs that lower your glucose, and we will be looking for the long-term complications if they exist. So pretty much all these things in green, we'll be looking for them as we assess the cohort. And with that, I will go to the, this one? Okay, so what you see here is cohort diagnostics, the results of cohort diagnostics published at the data.odyssey.org, something that we ran, or Gowtham ran yesterday overnight. And we'll be looking at the, let me first orient you what you actually see on the screen. So on your left side, you see a bunch of different types of tabs, and we will go through these tabs one by one. And then we have all sorts of cohort definitions that were ran here in the center, and we will start by looking at type 2 diabetes, inclusion of at least one occurrence of the code. And we will start with the cohort definition, and this is the first thing that you, in fact, can examine here. And the things that you can see is the counts. As we said, there are 4 databases that we ran these diagnostics on. There are 2 international databases, 2 European databases, and 2 US databases. The first and the second, France and Germany, are the PCP data sources. Not PCP, but
The IQVIA team here.
the,
Is anybody from IQVIA in the room?
not primary care, but yeah, that's the word I was looking for.
So for the IQVIA Disease Analyzer Germany database is primarily GPs, but also some specialty care. And then the IQVIA Disease Analyzer France database is general practitioner data in France.
Yeah, I was looking for general practitioner. Thank you. And then we have an EHR data source, Optum EHR, and Optum date of death, right? And we can see first of all, we can see the counts of the cohort here. Other things that we can examine is actual cohort definition. So we said that this is just one occurrence of any of the codes from the concept set that we built yesterday, a broad concept set, right? You can also use cohort diagnostics to export cohort definitions as well, which we'll not be doing right now, right? But the first thing, as we said, is we want to look at the codes that are observed in the data for this cohort. So we can choose a couple of databases just not to have too many stuff on our screen. And we will choose type 2 diabetes, single code. So what this will tell us is the number of patients, and we can also choose records or patients, the number of patients that have a given code from the concept set that we had. And if we look at it, we will see, well, first of all, you know, these databases and cohorts are very different in size. But if we look at the most common things that those patients have, we will see that, in fact, the top things that they have are type 2 diabetes mellitus code. codes. So yesterday we were quite worried that people that we include with diabetes mellitus may have other types of diabetes and not type 2. But in fact, if we look at the top codes that these groups have so far, we would see that the top 3 have explicitly tell us that these are type 2 codes. And in the very same manner, you can examine other things that you can see here, but basically so far it's pretty much straightforward. It's all sorts of diabetes that we have previously observed yesterday. We can also look at the orphan concepts. These are very much similar to what we were trying to do yesterday with Phoebe, when we were looking at the things that we may get recommended, at the concepts that we might have missed. And this uses parts of the Phoebe to do a very similar task. And if we look at the things it suggests, here you can also choose whether you want to look at ICD codes or standard terms or standard or source terms, and you can also choose whether to look at people or records. And what is nice here is that yesterday we were looking at the data from a network, from 22 data sources, right? We did not have information about specific data sources. Here, the concepts that you can see in the counts represent a specific data source, right? So if you're interested in running a study on your own data, this tab will provide you more information about your specific data source and can give you more insights in terms of what you have missed. Of course, then you will need to reiterate and run the cohort diagnostics again, but that's another thing. And if you look at the things that were not included, I don't think we want to iterate again to include any of them, because we definitely don't want diabetes screening, as it does not provide any results of whether the screening was positive or not. We don't want family history. We don't want prediabetes. We don't want type 1 diabetes. Type 1 don't want, secondary, gestational, all of the things that we explicitly excluded. So it's nice that on this tab, we do not really see any of the conditions that, or codes that we could have added but didn't. But again, as I said, in general, this tab is useful to see the numbers from your given specific data source. So with that, we can say that we are fine with the concept sets, right? Now let's look at the actual counts again, and we will go to the cohort we're looking for. And here we can, in fact, select all of the data sources, because why not? Oh, this is how it goes. So basically what we see here is that the smallest cohort that we have is was created on the DA France, and it includes 74,000 people. And then as we go further, in Germany it's 1,400,000, and then in Optum it's 10 million and 8 million. So these are large cohorts, and even the smallest cohort, 74,000, is big enough for us to look at. So that's already nice. Of course, if you are comparing different cohorts, you will see different counts here as well. But about that later on. The next thing that we want to look at is different patterns in the cohort. One of the patterns that we want to look at is demographics, of course, because this is one of the basic characteristics that you can explore. And as we said in our clinical description, we expect more males than females, and we expect the prevalence or the incidence of condition to increase with age, right? So we expect fewer people to be in the cohort when they're young and more people in the cohort of slightly older age. And this is what we will be looking at now. So this is the same cohort, and we're looking at 4 different databases. Oh, sure.
Diana, if I recall correct, yesterday we had an exclusion of the age younger than assumption, there will be people in the age category from 10 to 19 because we didn't exclude below 19 and lower. And therefore, is it possible to have that kind of age ranges align with the exclusion you've made?
Well, right now, we haven't made any exclusions, because right now the cohort definition is just one occurrence of a code in the concept set that we created.
So that was a
Yeah.
different kind of definition then that we made.
Yeah, we made
Well,
like a
well,
simple one
yeah.
and a more complex one.
Oh,
So,
okay,
yeah,
so
Yeah.
I'm confused.
yeah,
over that.
but I think your points are like, here, we're just showing age in 10-year
Yeah.
buckets.
Yeah.
So yeah, in this case, if you had applied a restriction of less than 18, then if you see people in the block, you know that they're 19 in this
Yeah,
particular
yeah,
case.
exactly, yeah.
Is there a way to change the age ranges, for example, here, or it's not a
You mean in the visualizations? Yeah, no, you cannot.
Yeah, these are the default values.
Which are buckets of 10. And what, what we can actually see here is that in all of the databases, so orange is male, green is female, purple is unknown sex. Not fluid unknown. Fluid is different. And we can see that, in fact, well, if we we actually do not want to look at unknown sex because it just confuses us, right? So if we regenerate the plot for just males and females, we see that in every database, we observe that there are more males than females in almost each of the age groups, and then the incidence increases with age, peaking at 60 to 79. So first, that agrees with our clinical knowledge, and B, that agrees with the clinical definition that we wrote. So that's already nice. We do not observe any, yeah. Oh, thanks.
The age is an index image, right?
This is the age at the index, yes.
The denominator is people with at least one observation. But calculating the denominator is people at least one observation.
The people who have, yes, not one, well, the people who are in the database, which means that they have an observation period, right? This is the denominator. So observation, at least one probably visit or code or what have you. But that very much depends on how the observation periods were constructed for that database. So for claims, it can be people who had insurance, and then for EHRs, it's whatever they please. Yes, the age here is defined at the index date. So basically when they enter the cohort, right? And at this point, we are not claiming that this is their very first occurrence of diabetes ever in their history. This is something that we will have to explore later on. Right now, it's just when they enter the cohort. Yeah. The data or? Well, the cohort diagnostics is an open source tool, all right? So you can always go to the GitHub and check out the code. It uses a feature extraction package. So if you want to tweak something, you can also collaborate with the people who maintain feature extraction to propose different age brackets. And that would be much easier and more efficient than trying to tweak it on your own. And this is one of the quintessential packages for all of the things in OHDSI. So I would imagine that it would not be that straightforward, but there has been interest for trying to get different age groups easily. So maybe that's an opportunity to actually collaborate there.
It's easy to change the default values, just like you just have to be able to pass the feature extraction parameter. But I do want to reinforce one thing that's really important. This tool is for the purposes of evaluating a phenotype. Like, based on a couple of the comments, like, it sounds like people wanted, like, jump to using these incidence rates as the answer to a question. there's a proper package for calculating incidence rates correctly. That's not this. This tool is only for the purposes of just trying to assess whether or not your phenotype's good. So when you look at these numbers, it's to give you that relative barometer, exactly as Anna said, like, is the age distribution going in the right direction? Is the gender distribution going in the right direction? Is time going in the right direction? That's the scope of this. That's to determine that your phenotype's good enough so that you can then go to all the other packages and start generating reliable evidence. And that's where things like what exact age buckets you would want would matter. Choosing your age buckets does not matter at the point of this evaluation, but it does matter if you're trying to calculate the incidence of a specific age group, in which case the tool that does that is fully parameterized for age and allows you to do whatever it is that you'd like to do.
So it's an emotion tool that gives you a good feeling or a bad feeling?
Yeah, so it is for the purposes of just evaluation. Do you like the definition, yes or no? And we very purposely try to treat this like as a stage gate activity. You don't want to be in the middle of determining whether or not you like your cohort and trying to interpret the results, because that could actually bias you as an investigator. Instead, we want you to only be thinking, is the phenotype good or bad? And once you hit the point that you decide a phenotype's good, then transition to say, given that the phenotype's good, let me design the study that I'm going to use the phenotype to calculate an answer. And we want to very deliberately partition those things out, because otherwise you'll get into the game of, I don't know if my phenotype's good, but I'm now looking at this incidence. I wonder whether I should report this. And we really want to separate those things.
Patrick, if I expand, is it also something that you just check off, something like maybe a 4 eyes principle, that you created a phenotype, somebody else is evaluating and says, okay, this is kind of fine, and I just have a check mark, go ahead with the research?
Well,
is that also in here or not?
Yeah, but I don't, the only correction is that I don't want to frame it as I feel good about it. I think what this is about is that you have an idea of, a clinical idea that you want to assess, right? And that can be defined by your clinical description or something else. And then you want to objectively compare what you see in the data to that definition. So it's not really, it can be about feeling. I just want to make sure that we're on the same page here, that we're not talking about some subjective feeling. We want to objectify it as much as possible. And therefore, we will be looking at the things and comparing them to our clinical description so that we can.
But you still got the question, right? So you still got the research question, just so you don't know exactly what the outcome is, but you have an idea of what the outcome should be because of, based on
Yes,
historical things. So it's not an absolute measure from, okay, good or bad. It's an idea that it
Yes.
could be good, and it's an idea that it could be bad, and you have to do rework.
Yes.
So in my opinion, it's a feeling.
Yeah. So just to add to that and to reframe your question, So some of this can be truly objective, quantified values that we can determine, pre-specify and determine. Some of it actually involves expert adjudication of information to decide whether or not it's sufficiently consistent with expectations. To your question about, like, do we do this like 4 eyes principle? So the work that Gowtham's leading in the phenotype work group, part of it is that not only do you produce a definition, but you produce an evaluation of the definition. So you write a document that says, this is what I learned. What the phenotype work group's also advocating is that you do an independent peer review. You have somebody else who looks at the information and says, yes, I agree with that consistent representation. That degree of rigor of how you do that qualitative assessment is something that we as a community need to come to terms with, because some of this thing, there is no precise quantitative value for the, in this particular case, there's no one exactly correct number that one could use as a reference, but there is some sort of expert adjudication that one could look at to say, is this directionally consistent with expectations?
Yeah, and if I expand one time more upon this, that from software development practices, you have something like behavioral-driven or test-driven design, and that's kind of like this, that you write your tests or the kind of behavior you want to have up front before you even create that phenotype, etc., and check your outcome against that test or that behavior, that risk behavior, and that sounds a lot like this.
Yeah, and that the medRxiv paper that Anna referenced, what Gowtham tries to do in that paper is to highlight the ways you could think about going through these steps a priori, even without knowing what the phenotype is. And that's what Anna's trying to walk you through right now with type 2 diabetes, so that when you all break up at your exercise, you're just thinking, okay, I know I'm going to do these tasks. Let me just march through them one by one and reason my way through whether or not my phenotype's appropriate.
All right. That's a nice conversation. We also should watch out time. Another thing that, well, now I feel like I have a lot to say about this conversation and continue that. But anyway, let's first continue the demo. So we can assess demographics, right, and whether that aligns with what we expect from this cohort and from this condition. Another thing that we can look at is the temporal trends. Now, the temporal trends, you, again, can see what is expected. For example, that condition overall is reported to be increased in incidence over years. This is not what we really see here, but other things that actually this plot can tell you is whether there are problems with any specific problems with the data. If you have weird spikes or weird drops, then maybe this is something you want to look more into. A classic example from the US data is that in 2015-2016, we switched from ICD-9 to ICD-10. So if you have, for example, different spikes or drops in incidence across in those years, that may indicate that your concept set is not balanced to have both ICD-9s and ICD-10s, or maybe it has more of the ICD-9 codes or more of the ICD-10 codes. Here it's just weird. In German and French data, we have a lot of people entering, and probably that's the beginning of the database, so they were just, a bunch of people were recorded at the same time in the same year, and this is why we have spikes in the very beginning. But then it's sort of uniform, and then we have drop, and we usually have drops everywhere because the data ends and all of the patient counts drop. So except for the spike in the beginning, the other patterns are more or less fine, except for maybe, this is Optum DOD, where in 2018 we have a slight drop, so we may want to examine that more in general and see what's going on in the data more closely. But for the interest of time, we will not do that now. Another thing that we can also look at is the distribution of the time that people spent, first the distribution of time that people were in the database before they started, before they entered the cohort, and the time they have in the database after, or in the database after they enter the cohort. So this is the last plot. The second or the middle plot is the time they spent in the database before they started, and then the first plot shows the time that they are in the cohort. And these plots can be useful to us if we have some sort of expectation of how long the cohort duration or era should be, right? If, for example, we expect we're looking for people with acute condition, and we expect the duration of cohort or the time people spend in the cohort to be short, this is something we can examine here. Because we said in this very specific cohort that people enter when they have an occurrence of code and exit at the end of observation period, of course the time they spent in cohort is large. And here, in fact, the median is 693 days in one of the databases, and even, around 600 days or 2 years across the databases. So then we can, again, assess whether that is satisfactory and whether that aligns with our expectation, which I think it does. And one of the cohorts has 1,289 days, which roughly corresponds to 4 years, which means that people, after they enter the cohort, have 4 years in the cohort. I personally find this page to be particularly useful if you are looking for very specific cohort duration, especially with acute events. Yeah.
So we haven't
Mm-hmm. 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 And leaves, well, and leaves the cohort, right? Yeah, and, well, well, this is, yeah, I said leaves the database is not necessarily the most accurate way to describe it. Or this person observation period ends. And usually somebody's observation period ends when they're dead or when they're no longer observed in a given database. And that can be for various reasons. As I said, if it's EHR data, then you would have rules of how your people are observed in this healthcare institution, for example. And their observation period may end when they, for example, well, usually it only ends when they die for EHRs. Then for claims, their observation period ends when they no longer have a certain insurance, right? So then their observation period may end when they're moved to a different insurer, or they switch to different plans, or they died, right? So
Is it the observation period, or is it the time when what we define for the cohort? So if we would define the end of period as, I don't know, remission of disease or something like that, would we see it here?
Oh, yeah, that reflects the time between the cohort start and cohort end. In this cohort, we defined it as the end of observation period, but if you defined it as, for example, for depression, remission or something, right? This is how you defined it. Then you will see the time that you presumably think the patient had a condition before they entered the remission. And that would be the last question before I move on. Yes.
Oh, sorry.
No, you're good. We just want to make sure that.
A more relevant question. I was wondering, how much is it related towards the plot you shown us previously?
Yeah.
Because then in France you saw
Yeah.
a spike at the beginning, and is that the beginning of the entry in the database? Is it the beginning of an observational period? Is it the beginning of the condition? Or how do this thing relate, and what is the effect of this one on the one you showed us yet?
No, that's a very good question. So if we look at France, we essentially have spike at 2017. So this is where the observation period, actually this is where the database starts, right? So you can imagine that there was a bulk of patients who had the condition in the very beginning. Like, for example, so if you have a database that started collecting their data in a given year, right? So what they did, I'm imagining that, but you can think of this type of thing. They took all of the paper records of the people who had conditions and stuff and who were observed, and then they put it in the computer, and this is where the database starts, right? And then they continuously input patient data as they move forward. So you would naturally have this spike in the very beginning, because this is where they sort of transferred all of the people in their database, if that makes sense.
The beginning of the database, so the entry point in the database, not the entry point of the condition.
Well, this is what is recorded in the data. We don't know yet whether this is the time where people had diabetes for the very first time. This is, as I said again, we will explore later on. Whether we see any signs of people having the disease before they entered the cohort. But this plot does correspond to what you see later on in the way that, for example, here the time spans from 2017 to 2022, so that's 5 years, right? And if you go to this plot, you would see, and this is France, right? You would see that people have on average 2 years, right? That's 2 years of being in the cohort. And you would imagine that as you have more time, you would have people that have more time in the cohort, right? If you only have 2 years of observed data, then your cohort cannot be longer than 2 years, if that makes sense. So these plots, in fact, do correspond to what we've seen before, in the way that DAF France covers fewer years than Optum DOD. So naturally, people will spend less time, potentially, in the cohorts, in the cohort than in Optum DID, because Optum DID simply has more time in the data. Yeah. Right now? I had some of the things that I wanted to show before that, because we don't have time. All right, okay. Since we're talking about Optum DID, let's do Optum DID. Anyway, we want to look at the patient characteristics. All right, the other things that we haven't touched that, but you can explore yourself is the visit context, which gives you the details of what types of visits people had when they entered the cohort, and index event breakdown, which will show you what of the inclusion or entry events got people into the cohort. But we want to move to the patient characterization, because that's one of the main things that you want to explore. And we will be looking at one database for simplicity. And here, the things that, first of all, we want to examine what sort of conditions those people have, right? And I want to just focus on conditions at one domain at a time. And first of all, we may want to look at the comorbidities, and this table is ordered by the proportion of people that have this condition, and let's group it by the time in different time windows. And I wonder if I can do that. Let's limit it to some of the times so that we can clearly see that. All right. So we're looking at the conditions, at the proportion of patients in the cohort who had these conditions, either in this time frame, which is roughly speaking within a year after they started and entered the cohort. And the second window we want to look at is the year before they entered the cohort. So we're essentially looking at the conditions that they had before and looking at the conditions that they had after. And let's first look at the things that those people had before they entered the cohort. So what we can, is that ordered right? No, that's not ordered right, just a second. So some of the things we can observe go back to our clinical description. We see that a high proportion of patients have essential hypertension before and after they entered the cohort. They have a high proportion of patients have hyperlipidemia, which again aligns with our clinical description. And then they also have all sorts of other things that do not necessarily have any relation with type 2 diabetes. But essentially here at the stage we want to look for their comorbidities, and also we want to look for the things that may be suggestive of low specificity, which in our case are things that should not be present in patients with type 2 diabetes. So again, based on our clinical description, that would be type 1 diabetes, that would be gestational diabetes, that would be secondary diabetes. So at this point, we want to make sure that our specificity does not suffer, and we do not observe people with the conditions that should not be here. So what we can do is we can, in fact, look for proportion of patients who, for example, have type 1 diabetes. And what we would see is that there are 5% of people who had diabetes type 1 after they entered the cohort, and 1.5% of people who had it before they entered the cohort. So here we want to consider now adding an inclusion criteria that says that people should not have type 1 diabetes before they enter the cohort, because we know that type 2 diabetes patients should not have that. And similarly, we can look at gestational diabetes or secondary diabetes, and we don't see any of that, but at least we want to make the exclusion criteria of people having no diabetes type 1 before they enter the cohort. We can also look at other things, and in this way, as we go through the different characteristics, we will be thinking about all of the things that will exclude patients from our cohort, all of the things that will make them not cases but controls. And this is where we would want to add, probably at this point, more exclusion criteria to our initial cohort to make sure that, for example, people with prior type 1 diabetes do not enter this cohort. Then other things that we can look at are, for example, drugs. And the expectation, again, based on our clinical description, is that people have treatments after they enter the cohort, right? They have metformin, they have other types of yeah, that's, let me just select all. Right, I did click on drug. And we'll be looking for people having treatments after they started the cohort. No, I'm doing that right. Yeah, please do. Yeah.
Yeah, so it's a good question, Eva, just to restate for everybody. So if we observe type 1 diabetes before and after, it raises the question, how should we specify the inclusion criteria in the cohort? And a consideration that one needs to consider is, what information do you know about a person at the time that you're making a decision that they should enter the cohort? So because we have this temporal logic that we're dealing with, we need to assess at the time that a person was diagnosed with type 2 diabetes, if that was the initial entry event, what did a clinician know at that point? And very often, for most of our studies, we would want to replicate what's actually happening in true clinical practice, which is you only know the stuff that's happened in the past up until that point to make a determination of a person's disease state. So that means you could know that they did not have type 1 in the past, but you wouldn't be able to predict into the future that they're not going to get type 1 in the future. Now, of course, a challenge that we have in this particular case is some chunk of patients get type 2 diabetes and subsequently identify type 1 diabetes. And if one believed that that future code of type 1 diabetes was the correct diagnosis, then that represents an additional type of specification error. That is, maybe the patient was worked up and had a differential diagnosis, and the endocrinologist finally figured out that they always had type 1 and just was misdiagnosed. So one could make some sort of choice to, in the cohort definition, look forward to say, we will not qualify someone if in the future they have type 1 diabetes. The concern that one needs to consider when developing that cohort is, what does it mean to use future information to determine the current health state of a given individual? And in many times, there's a danger about introducing some sort of immortal time bias if you're going to look into the future to determine someone's current state. But those are the exact kind of considerations that one would consider, is you're going to be trading off these biases or these errors that exist. If you don't throw away the people that are in the future, you may have some residual specificity error that you have a concern over. However, if you choose to get rid of them, then you may be introducing a different type of error into your process. And so those are the considerations that you want to be wrestling with as you're making these choices.
Yeah, absolutely, and we will continue this discussion after I'm done, I think, so that we have enough time to actually do the practice. Well, another thing, as I said, is we want to look at the treatment, because we expect these people, once they have diabetes, to get treated unless they can be on diet only, right? And here you can actually roll up to different levels of granularity. You can examine different specific drugs, or you can examine just groups of drugs. Here, I will just show you the the overall group of drugs that are used in diabetes, so that includes all glucose-lowering drugs. And what we can see here, it essentially shows you the proportion of patients that are taking those drugs on day 0, so when they enter the cohort, is here, on day 0, and then in the previous year, and then in the year after. So we see that when people are diagnosed with diabetes, 42% of them get treatment right away on day 0. Then half of this cohort has treatments a year after. So we can compare that again with what we expect from this cohort. But what is also interesting is that almost 15% of patients had these drugs in a year before they entered the cohort. So that potentially indicates that we're having index event misspecification, where patients in fact had condition before they entered, but we're not registering it. So here we may think of adding another entry event, which would be people will enter the cohort when they have either a condition code or a treatment for diabetes. And in a similar fashion, another thing, as we said, another thing that we said can be used to identify those patients is their lab tests. So we also can look at the patients who got specific tests for diabetes at the index date before and after, right? And this is all of the information we're getting from clinical description. And one of the things we said is used to diagnose diabetes is hemoglobin A1C measurement. Now here it does not give you the actual results, but at least it tells us that those people had this test. And what we see is that on day 0, there are 37% of patients who had this test, and then 11.5% of patients had measurement of hemoglobin A1C within a year prior. So again, it doesn't tell us that these measurements were above the reference range, but what it does tell us is that potentially we can add that as another alternative cohort entry event, where we would say that patients can enter the cohort on condition or drug for diabetes or hemoglobin A1C higher than the reference range, right? So that sort of indicates that we can improve our index event misspecification. And other things that we can explore here, but we will not know, are also procedures, and procedures devices is not common, or visits to do that in a similar fashion. Take our definition, look for the things that you have in a definition, and compare them to your baseline expectation. So far what we learned is that there potentially is the problem with specificity, because people have the conditions of exclusion, type 1 diabetes, before they enter the cohort, and we have problem here with index event misspecification, where people potentially had the condition before they entered the cohort. So these are the things that we can actually improve, right? And if we go back to our cohort definitions, this is what we did with this definition. We modified it in the way that now the entry event is a condition, as it was, or an exposure to drugs used for diabetes, or the measurement of hemoglobin A1C above reference range. So this is everything that we learned from cohort diagnostics. We now are implementing that as another cohort definition that we think should be better. And then we're excluding the things that we observed that can decrease our specificity, which is excluding patients with type 1 diabetes and excluding patients with secondary diabetes. And now, at this point, we in fact can compare the cohorts, because now we have two cohorts. One is more simple, another is more complex, that is built off of what we learned so far. And I will just show how you can explore and compare two different cohorts, and then we will be off to the exercise. So we can look at the cohort overlap, or how many patients are observed in either or both of the cohorts. And we will select our naive definition, and then we will select the second definition. And what we can see, dark purple is the first definition, no, dark purple is the second definition, and light purple is the first definition. And we see that now we're getting less patients because we added all of this restriction inclusion criteria, but all of the patients in the second cohort are subsumed and are in the first cohort. So we essentially just removed some of the patients. We did not add any new patients. And we can also compare their characteristics, which I'm not going to show I'm not going to show it in a lot of detail, but essentially, if you go to compare characterization, it does comparison of characterization between two cohorts. Yeah. And you can, again, choose any of the data sources that you like. These are also different data sources. And coming back to the question that somebody asked, if whether this one phenotype that we created will be fit for use for all of the databases we're running that on, this essentially will be also able to give you this answer because you can compare different databases. And let me do, for example, a year prior and a year after and day 0. These plots will tell you how different your cohorts are and if all of the dots are separate characteristics of patients or separate events in their histories. And then the diagonal line represents this equilibrium where the proportion of patients with a given characteristic is the same in your target cohort and comparator cohort, so in your cohort 1 and cohort 2. So for example, on day here, after they entered the cohort, this is the very last plot, we see that all of the dots are on the diagonal line. That effectively means that those patients look very similar in cohort 1 and cohort 2 after they enter the cohort. But then if we look, for example, at day 0, at the day that they entered the cohort, we would observe the differences. And the further away the dots are from this diagonal line, the more different the cohorts are in regard of these characteristics. For example, one of the things we can see is that our comparator cohort, which is just one condition code, has, just a second, I'm looking comparator. The cohort that is just one code of just the condition codes has many patients that have drugs for diabetes in the year before they enter the cohort, which makes sense because one of the inclusion criteria in our second cohort was drugs used for diabetes. So naturally, this would be one of the characteristics that we expect to be different. And you can explore this using the plots, or you can explore this using tables as well, if that's more convenient. But basically, if we had more time, we would just go over these characteristics and see if they align with what we wanted to achieve. I will just tell you that, yes, they align with what we want to achieve. And similarly, you can go to just plain cohort characterization and examine patient characteristics for the second cohort to see if we have any more problems with specificity or index event misspecification.
So Anna just gave you guys a whirlwind tour through cohort diagnostics. The main primary motivation here is for you guys to understand that there's this tool. There's a website you go to, and you can click around and explore all your cohorts. What you might have seen is this very same web page that you're looking at here has not just the diabetes cohorts, but all those cohorts you guys created last night or yesterday afternoon. The only thing that's changed is we just had cleaned up the descriptions of them so that you're now, it's going to say OHDSI U, your team number, and then the description of the cohort. What we want you to do, and actually I'm going to go to the slide to orient this here. So what we're going to do now is we're going to break up into our groups, but rather than you break it up in your small groups, there were 2 teams assigned each of these phenotypes. So team 1 and team 11. Raise your hand if you're on team 1 and team 11. You lost all your friends. Okay. All right. So team 1 and team 11, you guys are now one team. You're team glaucoma. And you are gonna get together as a group, and now you are gonna be able to evaluate your own definitions that you created, but compare the two definitions that you created. And so as Anna showed you, you can go through the cohort definitions one by one, but you could also just stack them up next to each other and see how they compare and contrast. And so we want you to, as one group, work through that. Team 2 and Team 12 who had fatigue syndrome, raise your hands. We got 2 and 2, okay, you guys have made a team before, that'll work, so make sure you guys get together. Raise your hand if you're 3 and 13, doing NASH. All right, you guys are scattered about, okay, see who your team is. You guys are gonna be together. Team 4 and 14, colorectal cancer. What happened there? Are you guys 4 or 14? You guys are 14? There's no 4. I never liked team 4 anyway. All right, well, you guys can evaluate your definition and see how much better it is than that horrible other team. So you'll be able to see theirs in there. Psoriasis, team 5 and 15. Got up there and over there, okay, you guys can connect up, see how you're doing there. Team 6 and 16, working on type 1 diabetes. Team all the way back there, a cluster over here. You see each other? Okay, good. Team 7, 17, herpes. All right, we got 2 clusters. All right. Team 8 and 18, erectile dysfunction. Got one very proud hand up and everybody else a little sheepish about it. All right, very good. Okay, you guys can connect up there. Breast cancer, 9 and 19. Down here and over there, very good. And depression, 10 and 20. All right, you guys see it good. Okay, so logistically, the thing that you're gonna see here, and let me go to the URL and I'll put it up here, and I'm gonna paste it on the slide so that you can see it, is you guys have the same clinical description. You have the same, let me just paste it here. Okay. Make this bigger for you all. Hopefully you guys can see this and I'll be able to show you how to get to the URL quickly enough. So there is a URL here, data.odyssey.org/EU Symposium Phenotype Tutorial, and then you're gonna see a number after it, 01. We actually created 10 copies of this website so that, what's that? Well, we only need 10 for this. So your team number is now going to be the first number of the 10, 1 through 10, okay? So if you were 6 and 16, you're going to go to 06, okay? And this is just so that you guys don't collide and break down the server. You got 10 different websites, one for each of your teams, and they're going to go from 01 all the way to 10 that you can go to that website and be able to play around with. You are welcome to sit in here as a group. You'll probably find it more comfortable if you go out to grab one of those tables downstairs. We've got, I want to give you guys as much time as possible, but I want you guys to come back, and each of the 10 groups is going to report out the 3 most important nuggets you learned by doing this, okay? So I'm going to say that we'll come back at 12:30. Yeah. So we gave them 45 minutes. So come back at 12. So you guys have 45 minutes now to go work as a group. Come back here at 12 o'clock promptly so that we can have everybody report back. And Anna and Victor and I will be wandering around and check in on you guys to see how you're doing. Just going to remind you all what your assignment's going to be. Going to have each group come up. Want you to share 3 insights, something you learned. Ultimately, what I want to hear is, do you think you've got a phenotype that's currently ready for the phenotype library? Or is there something that you learned that you feel like you need to make an iteration on? And then would love to hear what other insights that you guys gained. It could be an insight about the clinical idea and what you learned about the phenotype. It could be an insight about using the tool. It could be an insight about the data, whatever you want. I want you guys to share 3 pearls of wisdom with each of us, and we're going to go through all of the teams real quickly to share those. If it's not too much of a pain, I'll suggest that every team just pick your one representative who's going to talk on behalf of the group, and you guys can just come up and share the mic so that we get it recorded for the session, okay? So everybody send one delegate down, Every team got one person coming down? Now, yes. So I should have 10 people up here with us. All right.
And we have the microphone here.
I know, but it'll be easier if they just go. All right, so we got 1. I got 2, 3, 4. You're 7. Very good. All right. Do I have a representative for the glaucoma team?
Yeah.
You got, okay. All right.
Okay, so we saw that there was good concordance between the two definitions. We did have a question, though, when we see the dots that are not on the line, how do we understand what's contributing to that? So that you could answer that question later. And then the second point was that France had very small number of counts, and that perhaps we need to understand how France codes this diagnosis compared to the other. And then the third one was there was a very, very large number of counts in Optum that, we don't know what's the total, we didn't know the denominator of records, but if it's like higher than 2%, which is expected to be the incidence, then perhaps we don't have a very specific definition that maybe we have good sensitivity, but not good specificity. That's it.
Thank you, Cynthia. And just to answer your comment there, so I saw several of the teams were using the compare characterization tool, and as a default, when you open it up, it shows a plot with the dots on the 45-degree line like Anna showed. So if you hover over a dot, it'll tell you what specific condition you're seeing there. But there's also a tabular view. It's the exact same content, but for those that like to see the table, you can just read the rows one at a time and sort by the standardized mean difference, which just tells you what are the big differences that you see there. Great. Do we have team fatigue?
So for chronic fatigue syndrome, it was really hard actually doing it because we tried to put all the people that had chronic fatigue diagnosed and then people that had fatigue, malaise, and all other stuff. So I was actually from team 12, and it was really hard to know from fatigue which ones could also be part of chronic fatigue, because we have, for example, fatigue for cancer. Does that mean it could also have chronic fatigue, or we don't count that? So then when we reunited with team number 2, where there was a doctor, it was easier because she knew a lot about it, and we realized that our cohort was way worse than theirs. And we saw that people from 40 to 90 have chronic fatigue syndrome, especially in the gap from 80 to 90 years old. There are way more women than men, and we still have to take in count, in 2015, there were way less records, and we talked with Anna, and she explained to us that it's probably because of the code change, and we need to take care of that. And we had to add different stuff that we weren't taking in count.
Awesome. Great. I mean, just the time trend there is a really good one to show. So I'll just show what you're, thank you for that. That's really wonderful. I'm going to just go to that one because I think it's a very nice illustration. So if you go to the incidence rate tab, and can you remind me which, that was 2 and 12, right? Team 2. All right, team 2, there we go. Chronic fatigue syndrome. And I'm going to select all the databases. And I'm going to plot the incidence. And so remember, we've got 2 databases from France and Germany, and then 2 databases from the US. And one of the things that you observe, which just shows this very striking pattern, is the 2 databases from the US seem to have this very small incidence, and then all of a sudden it magically jumps up, and then it seems like it stays kind of stable, and then something weird must have happened in 2020, I don't know. In this particular context, you see this type of pattern, and this should absolutely give you pause when you look at it, because it should make you think about, okay, if there's a dramatic change, is that biologically real, or is that going to be some sort of a data artifact? And so if I were to be thinking about chronic fatigue syndrome and wanting to use these US databases, I would either need to figure out how can I change the definition to cover this continuity of time, Or I may actually make the decision that I can't use this definition prior to 2016, and I'm going to have to actually restrict my study to 2016 onward. But that's the kind of insight that you can gain when you look at this information. Awesome. Great. Team Nash.
So yeah, hi. Well, first of all, you shouldn't be too exclusive. For example, we had a measurement we added which seemed like completely needed, but it excluded all of the otherwise included patients. Second of all, I think you should really like mind your databases or data sets where are you going to run your cohort, because not everyone have everything mapped. And maybe third of all, you should really have like a medical doctor's expertise once you're only a data scientist, for example, yourself, because it's not really as easy as it seems. Yeah, thanks.
Great, awesome. So Team Nash was the only team that got the opportunity to create a definition that produced 0 people in all 4 databases. But it's good that you were able to identify why that happened, which is great. And I'll say that that'll be the last time that I will accept the phrase "only a data scientist" at any OHDSI event. The clinicians need you a lot more than you need them, or you should probably need each other. But I definitely agree that this is part of the reason we try to create these tools is to create a collaborative environment. And I think the reality is we need both sets of skills to be able to do this effectively. Great. Team colorectal cancer?
I believe they all left for the...
Aren't you guys colorectal cancer? Don't all run up here at once. One of you guys come down. I'm totally willing to accept awkward silence until one of you come down.
Right, colorectal cancer. What did we learn? Our definition, so we compared the number of patients in both these groups, and our group came out as, I think, 5 million. The other group came out at 400,000, so there's quite a big difference between them. And then we looked into the individual codes that bring people in, and we found that our group included benign cancers as well, which included quite a lot of the patients. What else did we learn? The age group was slightly younger for, the age distribution was slightly younger for our group, which I think is in line with what we were thinking about the benign cancers, and we also found that there's a bit of a jump between 40 and 50, which might be explained by screening. What else did we learn? Anything else from the team? I think we're all good.
Great, thank you. So that's actually the good example of the benign tumor. So in the SNOMED hierarchy, when you're looking at various cancers, you can select something like a malignant tumor of organ class, or you can select something just like tumor of, or just neoplasm of, and you do have to be mindful of whether or not you actually want to be pulling in the benign things. And of course, in colorectal cancer, you get all sorts of just benign polyps that'll show up. So it's good that you were able to identify that and figure out why that's happening. That's great. Wonderful. Team psoriasis.
Hello. About the lesson learning for today, we have compared the two core definitions. We realized that more or less the numbers were kind of matching, although the group 15 had more comprehensive core definition and concept sets. So we started really digging in, trying to understand what were the differences in the different definitions that we had. And so we started really probably looking too much into the details, but then we realized that comparing the two cohorts and the type of patients that we have selected, they were acting the same. They had the same comorbidities before and after. and so really probably an understanding of what was the difference between the sensitivity and specificity, I think, in that type of code definition. So the lesson learned is like, not necessarily we need to be hyper-precise in a type of patient's population a priori. So I think it's like most of the information will come later in terms of like the applications that we wanted to use and to have. So yeah, mainly that's the big lesson learned.
Very good. Thank you. I think the psoriasis team also did a nice little experiment that I encourage you to take a look at. They had one definition that just was a single code, and then they had a second definition that required 2 or more diagnosis codes. And so you could actually see that sensitivity, specificity trade-off, which is a nice one that you can evaluate. All right, type 1 diabetes team.
So the step which we take for the future work is actually that we really need, the first step when we increase the sensitivity, we really should not restrict the only one domain for, like, say, condition. We also should consider other domains, because some like databases have different proportion of diagnosis there. So it is the idea to consider for future work. Another thing is really, it is a really nice idea to compare different cohorts so that you can see the differences in logic and therefore make your cohort bigger and more precise. And another thing is that when you define your cohort, you really need to know about your disease. You really need to know that age occurrence is like this or that, and then see it in the cohort diagnosis. That's it.
Awesome. Great. Thank you. All right. Team herpes. Zoster, that is.
Yeah. Hi, I'm here representing Team 7 and 17. We had 2 very different scopes on this exercise. Team 17 went for a very specific set of condition codes, a very narrow set, and no other conditions. And Team 7 added a treatment concept set. So when we compared both cohorts, we saw that one was probably too sensitive and the other was probably too specific, because one was completely contained inside of the other, but in the bigger one, there were some codes that were not there. So probably the sweet spot is closer to the more sensitive than the more specific, but none of them is perfect, that's for sure.
Awesome. Great. That's a nice comparison to be able to see that, now that you've compared 2, you're able to figure out what that third idea is going to be that somewhere in between.
The variant comparison is helpful figuring this out, but we didn't get that far.
Very good. Awesome. All right. Team erectile dysfunction.
Yeah, so we had actually 3 parts, I think. We had something about the tool itself, the databases, and then the guidelines. So tool-wise, we were group 8 and 18. We noticed that in one we had 90,000 patients and the other about 4,000. But then I think the recommendation would be to just check your code and query very well, because apparently in the 4,000 group, we explained that by finding that number, we had not the condition included, but just the sildenafil kind of classes, so that's just the drugs. And we kind of assumed that explained that number. Then on the databases, we also found, and that's been mentioned as well, that for one you find 90,000 and for the other 0, so you would hope to have maybe some metadata as well on that, like why is it not finding what it should find? And 0 is quite an absolute number in that. And then guideline-wise, it's really hard, I think, to know what the clinical practices are around the world or in countries. So, for example, if you would think about like taking a lab measurement and then connect it to a condition, so like what is registered, you should know not just on like one paper what the actual status is and how doctors use this system, because you might like exclude or include way too many people. So you bring in or maybe bring out an error, but you cannot be too sure because you don't know how well it does represent the actual practices in the country. So I think that's it.
That's great.
Yeah, thanks.
Thank you. Yeah, I think actually erectile dysfunction probably provides a really rich example to think about cultural differences in data capture in terms of like where that will be diagnosed, how it will be treated, where that will be covered in terms of insurance coverage and that kind of thing. So it provides a nice demonstration of how there needs to be some knowledge about the regional areas. And part of what we would assert is a helpful use of this tool is that it's probably impossible for you to know what does erectile dysfunction look like in the 80 countries that have OMOP CDM instances, so you're not going to be able to know that everywhere. But if you have the ability to run a tool like this, you can start to learn and understand that a little bit better. Great. Team breast cancer.
The first point was that we found that the risk of the diagnosis code missing was not too large, at least for breast cancer. We had one of the groups included radiation therapy as an entry event, and that really didn't matter too much as compared to just having the diagnosis code. And then second of all, I think we learned how important it is with having the clinical knowledge, as you can be very coherent across the two cohorts you make and still be very wrong in the sense that estimating the time where the breast cancer was there. We had one group saying from diagnosis to the end of observation time, and then the other group had that, and if you had a full mastectomy removing the breast, then you would go out, and and that is, probably the breast cancer was stopped earlier in both cases, right? So even though the two cohorts were similar, it really wasn't very accurate on the duration of the condition being there. And then, what was the final point? Forgot, I think. Forgot. Yeah.
Awesome. Yeah. Thank you. Thank you, Team Breast Cancer. And last but not least, Team Depression. Ending on a downer.
Yeah. Yeah, so we had two a little bit different cohorts, which was very interesting, and we made, I think, the same observation as the herpes team did. So one of our depression cohorts was purely defined from the condition, and the other one was defined from condition plus medication. And the difference between the cohorts, at least in France and in US, was about twice as large a cohort for having both an antidepressant treatment or a diagnosis versus just having a diagnosis. Whereas in Germany it was only about a factor, I think it was 16 to 20 or something like that. And this is quite interesting because there's not really a good answer to which one is the correct. It's clear that the ones that only went on the diagnosis had a much greater specificity for depression-related diagnosis, of course. But the other one but we also know that most of these antidepressant drugs can have alternative treatment reasons. But I think one of the main reasons we actually see this pattern, especially in the US, is that we have quite a few patients who have an insurance only for pharmaceuticals and not for going to the doctor. And that means, of course, that we're not going to see any of the diagnosis. So it's something to sit and think over for a while, I think. And I can't say that any of them is the perfect one right now. The second point we came up with was both how nice it was to do this iteratively, so think out criteria, put them in and see what the consequences are, and then consult with clinicians. So we sort of get the data and the clinician to work together in harmony to make the best diagnosis. And I really think that is the way to get the optimal results eventually. A third point I will add is how it's very nice to have a clear idea of where you're going, and and I think that's something that one should try at least before starting to be as to think out as carefully as possible about exactly what it is you want. Yeah, yeah. Yep.
Very good. Thank you. All right. So we got 5 minutes, but I got to poll you all on a few things based on the stuff that you've heard from each other and as well as what we've covered. So actually, I'm going to start with the last point first. So clarity of idea of where you're going. So you've heard from Anna stressing this idea of you should have a clinical description that writes down exactly what is the target. So show of hands, how many of you, when you've read a paper, feel like you've had a clear clinical description in the manuscript you're reviewing? A couple hands, most people don't. Okay. How many of you feel like it should be in a paper that is written? Okay. So how many of you, moving forward when you're phenotyping, are going to write a clinical description? Okay, good. So raise your hand if you're going to write clinical descriptions moving forward. All right, Anna's capturing those that don't. All right. So, and actually, in all seriousness about this, within the OHDSI community right now, there is not consensus about this idea about a clinical description. I think for the most part, people would generally agree that it's better to have some idea of where you're going versus not. But the challenge is that clinical description, we provided you clinical descriptions, we provided you a reference, but it's not clear is that the right content? Is it too much? Is it too little? What is it supposed to include? What is it not supposed to include? So an area of opportunity and collaboration in our space is I think we should be able to agree that knowing where you're going is something we should do, but exactly what does that specification look like is something that we can work on together as a community. Yes?
Do you have any advice on how to report like the cohort definitions on scientific communication, on how we should convey that information in? Do you have any advice? Because I find it hard, and I think it's crucial if we want it to be reproducible, to be able to convey this information correctly.
Yeah, so it's a great question. So advice about how do we actually disseminate this information? So I think there's two things that we're trying to do as a community, and then I'll share my personal opinion about it. So as a community, we're trying to get everybody to collaborate in putting definitions into a phenotype library with the idea that the phenotype library itself will have a full clinical description, a full specification, and a full evaluation. And the idea is that can become itself a citable artifact. So there's a DOI associated with that. And so if it was in the phenotype library, you could say, we used the definition of depression from OHDSI, go read its clinical description, its definition, and its evaluation here. And that would actually help a lot because part of the constraint that I presume that you're going after is you only get a small paragraph and you want to put something in.
Supplementary data that is
Well, the second thing that we have been trying to do as a community is we've been really trying to push hard on transparency and not be subjected to word count limits in journals. So we do almost always, I think in all the papers I'm involved in, we always put a supplemental appendix with a full specification of the definition. And they can be obnoxious. Some of our supplements are hundreds of pages long, but part of that is because this stuff needs to be there. And if you don't have it, then what are you doing? That said, my personal commentary is I'm really proud of what the OHDSI community has been doing in the space of phenotyping because I juxtapose that to what's going on in the literature, and I feel like we are really adding a lot of rigor to things. That said, I don't think we've cracked the nut of phenotyping yet. I think that there's still a lot more we've got to figure out, not only in terms of development evaluation, but that dissemination piece. Because I think there are still real challenges that until the thing's actually a computable element that I can take and bring into my environment, we're still missing big opportunities for more meaningful scientific exchange.
If I may add one last comment,
Yeah.
I'm sorry, I think it's just the right time to discuss
Yep.
this. So, what do you think about having a framework, not necessarily in the context of OHDSI, but what do you think about having a framework for the clinical guidelines, have a machine-readable understanding of what is written there? We have also had very much difficulty translating things like dyslipidemia guidelines, European and American, in something that is machine readable and that can be implemented in defining cohorts. And if we could also have that more machine readable directly on the guidelines, if you feel that would also be a good thing, or if it has some other
Oh, I think there's a huge opportunity for us to collaborate with professional societies and guideline developers to try to figure out how to translate the clinical expertise into something that's functionally useful. Danny Prieto Alhambra and I were actually at a meeting just 2 weeks ago in France where we were meeting with folks from the Brighton Collaborative talking about adverse events of special interest, of which they've got a clinical team that are writing documents, but then the translation of the documents into something that's implemented is missing. And so we were actually talking about meaningfully, how could we provide operational definitions that would sit side by side with those definitions? So that's the same kind of thing that I think there's a good opportunity for collaboration there. Yeah, that's great. All right, so clinical descriptions, we look like we convinced a bunch of you about that. How many of you feel like you are more comfortable with creating concept sets now, given that we just did this? Show of hands. Okay, good. Okay. How many, actually, let me, a predecessor question. So how many of you have had to create code lists before for research? Some of you, many of you. Okay. All right. So what was it about what you went through yesterday and today that makes you feel better about it then, for those who've had to do it in the past? The recommendations? Okay. Phoebe, yeah. Looking at the different domains was helpful. Very good. Okay. So I strongly encourage you all, so if you are using OHDSI tools within your own institution, you've got a version of Atlas available. I strongly encourage you to use it. For me, the most powerful thing that we did was tying code set selection to record counts. Because it makes a big difference that you're not just theoretically looking up words and hoping that the words are going to match, but you can actually see whether or not the words correspond to something that actually shows up in the record. And for those of you who don't have a version of Atlas or don't or want to be able to use the whole network, the demo environment that you guys played with, that's publicly available. And as Anna said, like we put 23 databases combined together up there because it provides a mechanism to do that, which I think is very helpful. I can't tell you how many hours, days, weeks, maybe months I have burned unproductively having arguments with people about codes that don't exist in databases. That is not a useful time, but it's been a lot of time doing that. Instead, by being able to actually focus on what's going to matter, what's going to actually move the needle in terms of your numbers, that's very attractive to me anyway. Yes. Yeah, so the question was, if you install Atlas locally, can you do all of the same recommendations? Absolutely. So in fact, the Atlas demo version, that's the only place right now where there's that aggregated 22 data sets. But as a default, if you were to install Atlas locally and run it, whatever is your CDM is actually what the record counts are going to be pointing to. And so you can absolutely get those recommendations and the record counts based off of your data. Yep, and you just pick whichever databases you want to see. So at J&J, the way that I have things is we've got each of our individual databases. We've got like a dozen or so databases we license. And then what we've done is we've actually added together the counts across all of those databases into it's fake J&J network database that we look at. And that's exactly for this purpose of being able to like look across the databases all at the same time. But that's as a default, if you install Atlas and configure it to your own CDM, that's how it will work. Yeah, so if you want, if you have multiple databases and you want to combine them together, I'm happy to, it's a very simple script. So the record counts are coming from a tool called Achilles that everybody would run on your own individual database. To create the fake network of your own databases, literally you're just summing the counts of Achilles into a new Achilles that counts them up. So it's very easy. I'm happy to share details about that. Yeah, yeah. The question is, when you use record counts versus person counts. I guess it's a preference thing, but I personally don't care about the precision of the number. I just care about it in terms of directionality. And I use record counts specifically because when looking at the descendants, A record count makes sense when you do a descendant record count. You can sum up records, and that's totally fine. If you would do a person count, you can't really do a descendant person count because one person could have multiple codes within the ancestry. But really the main reason for it is directionality. So like as Anna showed with her 23 databases all have wildly different codes. I kind of just want to know which ones happen a lot, which ones happen a little, and which ones don't happen. And that's really what I'm really looking for when I use those numbers. For acute conditions? Yeah, so some diseases may show up, not only acute, the question was, does the record versus person count matter for acute conditions? So certainly diseases that are recurrent, you may see the codes multiple times, or even chronic diseases. Type 2 diabetes is, if a data set keeps entering it every time, you may see tons of that. But really the point is to decide, is the concept something you want to include or not include? Okay, yes? Yeah. Yeah. So the question is about the recommender tool right now. It's a manual review process, and so could we come up with some sort of algorithmic process to automate that further? That's a great opportunity for research. So you started your PhD 5 years ago? So when Anna started her PhD and made the mistake of working with me, I told her that I wanted to fully automate the phenotype process. She's now graduated with a distinguished PhD, and we came up with a recommender system. So it's a hard problem to fully automate that. I still, was it, or no, that's not true. So I would say it's a hard problem. I'm still optimistic that it can be done, but it is not clear. So one of the things we learned through the iterations we've done in developing the recommender system was that for every scenario and story you could tell yourself about why this would be a good recommendation, you could find another edge case where it was a bad recommendation. In the case of, we went through the type 2 diabetes, and the first recommender from patient context was hypertension. And that doesn't make sense if I'm trying to define diabetes, but it makes perfect sense if I say, what's the thing that's going to be most correlated with diabetes? It's going to be hypertension. And so all of these circumstances, it's really hard to come. We've struggled to find a very clear, objective rule. And so that's why we currently are in the position of, why don't we provide these options and let experts review and adjudicate them? But I'm very optimistic that there's more research to be done in that space. I'd love to see it not involve so much human review, for sure. You scared? Yeah. Mm-hmm. Yeah, it's a good one. So the comment was about breast cancer and whether we talk about general breast cancer, which would include women and men, but predominantly women, or whether we think specifically about a phenotype just for female breast cancer. And so that would be something I would argue is what needs to be in the clinical description that you align on, agreed. One can think about the biology of those two different diseases and whether or not they are of different composition, of different meaning, and that could be used to justify that clinical description. That in that particular case, the easy part is the implementation of it. Once you decide you're doing female only or both, it's easy to implement. The harder part is that clinical determination of what is it that you're really trying to target. All right, so we talked about concept sets, so cohort definitions. How many of you before this session had used Atlas to create a cohort definition? Okay, about half of you. Okay. How many of you moving forward will use Atlas to create cohort definitions? All right. A couple of you didn't raise your hand. So for those of you who or didn't raise their hand enthusiastically enough, so what was the challenge with creating cohort definitions in Atlas for folks? Yes.
One challenge was that I learned to do cohorts with
Got, yeah.
Now I'm looking at Atlas, looking for the function that I used when using R.
Got it. So you've been using like the Caper package? Yeah, so you got comfortable programmatically writing cohort definitions, and using a GUI is a little bit less intuitive.
Yeah, because I already know the code.
Yeah, understood.
You have to face the code, it's also a big task.
Yep. Cynthia? Yeah, so just one quick highlight. So if we pick a cohort definition, sorry, let me go to Atlas. If I go to any cohort definition, you can actually export the cohort definition. This is a JSON expression, and this JSON expression using the CIRC package will translate that directly into the SQL that will execute against your database. So this is fully end-to-end from user interface to a JSON file. From a JSON file translates to SQL. SQL will run against your common data model and populate the cohort table. So that's how all of this technically works. The comment that was made earlier, Martin Lavalle has developed a really nice package called Caper, which basically provides you an R programming interface. And what it will do is if you write R code, it will write the exact same JSON. What that means is you could take this JSON and you could write this JSON either through the interface or through R, and it will be the same specification. So a Caper JSON file can be imported into Atlas, and you could be able to use it that way as well. What that's particularly helpful for and very nice is if you really want to do a lot of like templating of cohorts, then it's really nice to be able to do it programmatically. If you're in that iterative process and trying to rapidly figure out whether or not you got the right concepts using the recommenders and stuff, then probably the UI will be a little bit more convenient for you. All right. Anybody else has a challenge with, yes?
I think that there are many functionalities, and that's of course a plus, but it can also turn out to be a minus.
Yep.
I think that for me at least, using Atlas is the second step, because the first step will always be to sit down and discuss and consider what it is basically you want to do.
Absolutely.
And I think we should be careful not to forget that.
Yep.
We could be lost in all these nice functionalities.
Yeah, that was a great point. Yeah, so we tried to, we started this thing by saying like, you got to write a clinical description, which is another way to say like, you need to start by knowing what you want to do. And it is potentially tempting to like jump into a tool and try to figure it out along the way. But if you don't know where you're going, then you're not going to necessarily get there. My personal bias, having been involved in trying to support the development of Atlas, is I think that the Atlas development team has done a spectacular job of creating a open source tool that, from my perspective, is more feature rich than all of the proprietary tools that various companies that I won't name that are charging you industry people $1 million a seat. You know which software they are. This is more feature rich than all of that. That said, very few of you are contributing to the development of Atlas. And you guys need to know that like Atlas is developed by basically like 5 guys working super hard to keep this afloat for the thousands of researchers around the world that are using it. And so if there are ideas for improving the user interface, improving the features, it would be great to hear it, and it'd be great to have more contributors to support that development. I think that the feature richness has made the user interface more complicated than a lot of those other tools that are on the market that you can spend $1 million on. But it's also those feature richness that make it possible to do things in this tool that you just can't do in any of the other proprietary tools that I've seen that are out there. All right, cohort definitions. I know we're over on lunch. I'm gonna get you to lunch. Cohort diagnostics. How many of you had used cohort diagnostics before this session? A few of you, okay. How many of you will use cohort diagnostics for all your phenotypes moving forward? All right, not everybody. So let me ask a different question. How many of you see the value in evaluating your phenotypes by looking at the data instead of just hoping that it's good? Okay, so everybody at least sees a value in that. Any thoughts, comments, reflections on cohort diagnostics and that evaluation process? Yes? Yeah, yeah. So you saw example in your group specifics. You had one that was more sensitive and one's more specific. And so like the challenge, of course, is you can keep iterating and try to find that sweet spot. I think to indirectly answer your question, my feeling is before going through this exercise, if you hadn't evaluated them, you would have guessed that one might have been more sensitive, or maybe guessed that one was more specific, or maybe not even known. And I would say that when I look at research, what gets me most discouraged is that there's assertions that phenotypes are okay without evidence to back it up. I would actually argue that just the knowledge of what your sensitivity and specificity is already a leap forward, because now that you know what your measurement area that you're dealing with is, you can think about the consequence of that error on your study. That said, we very much do see this as an iterative process. So like, if you create a definition and it's not achieving the desired error for your question, that gives you a chance to say, how can you make that change, go back and iterate and get to the point where it's of sufficient error. When we use cohort diagnostics, we were showing you to identify sources of error. I think one of the comments that was made earlier was about it's still a bit of a qualitative assessment. When we use a tool like Phi-Evaluator, where it actually estimates the sensitivity and specificity, then it's a little bit easier to have like a rule that says, I will accept a definition if it has sensitivity greater than 80% and PPV greater than 90% or what have you. I know, Peter. I'm going to let them go in just a second. Once I'm on the soapbox, you can't knock me off. Last thing. Did anybody get to a cohort that you're ready to contribute to the phenotype library? Nobody yet. Is anybody interested in carrying this forward to get to a contribution to the phenotype library? Couple hands. Okay. So I really want to sincerely encourage you to take that next step, and I'd be delighted to collaborate with you to do that. Our phenotype work group, like this is what we do, is we're trying to work as a community to create definitions that we can make available to everybody. I also encourage you, I know that it was a little bit artificial that we randomly assigned you diseases that you may not know about or care about. So I want you to consider now that you've learned this process, if you have your own areas of expertise and you want to develop a phenotype to go through the same process and contribute them to the community. The only way we're going to be able to grow and learn as a community is if we create this library of phenotypes that have gone through this process and make them available so that we can all benefit from them. So I want to encourage you all to do that. So it is odyssey.github.com/phenotype library. It's in our Odyssey Git repo, which is called Phenotype Library. And there's also just a link straight off of the Odyssey website. And the Phenotype work group is just one of the community work groups that you can join. And I'm pretty sure it's always Friday mornings that they have their work group meetings. At odyssey.org, you can actually see all the community work group meetings and the links to join all those. All right, I want to thank you all for participating in this workshop. I look forward to seeing you in the work group activities that are happening this afternoon and at the main symposium tomorrow on the SS Rotterdam. Thanks all for participating.